Hello, this is Mr. P, and today we're going to continue solving trigonometric equations and use some other trigonometric formulas, such as the sum and difference formulas and the multiple angle formulas, which for our purposes today will be double angle formulas. Now, starting with the sum and difference formulas, those are going to be useful to evaluate trig functions for angles that are not the ones we see on our unit circle. Maybe multiples or combinations of ones we see on the unit circle. So here we're going to look at the sine of a sum of two angles or the cosine of a sum or difference, that is, of two angles. The u and the v can represent either a variable or an expression, but they are taking the sine and cosine of an angle that we're going to measure in radians. All right, for the second one, you might notice this symbol here, and this is not a typo. It is minus or plus. It has the same meaning as the plus or minus symbol, just with a different order. So, for example here, if you have cosine of u plus v, in other words, if this one is a plus, then this one will be a minus. So by using both symbols, we can actually write the formula in a single line, rather than have to write it as two different formulas. So again, this does mean plus. This means plus or minus. This means minus or plus. All right, and for the multiple angle formulas, notice that for sine, our double angle, we have one choice, but for cosine, we actually have three choices, depending on what would get us closer to our goal algebraically. Notice how cosine of 2u can be cosine squared minus u squared. And then if you make substitutions, the fact that cosine squared is 1 minus sine squared, or sine squared is 1 minus cosine squared, you can derive the other two formulas, which will give you an expression that has just cosine if that's what you need, or if it has just sine if that's what you need. So let's start with the sum and difference formulas. Let's look at finding an exact value, so we're going to leave it in radical form if it does have one. Find the exact value of the sine of 7 pi over 12. Now normally that's not a denominator that we would work with. We can do any of the values where it's over 2, over 3, over 4, or over 6. We can work with any of those angles. But when you have 12 as the denominator, you're going to have to find a way to break that up so it's something we can work with. In other words, we're going to break this up into something over 12 and then plus or minus something else over 12. So the logic here is I want to think of the number 7 here. I want to break that up using addition or subtraction of two other numbers. And I want to choose these numbers so that they will reduce with 12. Ideally, we would want them to be a factor of 12. That way it would reduce fully to a quadrant 1 angle. But as long as it's something that can reduce the 12, then the 12 will become a 6, or it'll become a 4, or become something you can work with. So one that stands out to me is 4 and 3. 4 and 3 are both factors of 12, and if we say 4 pi plus 3 pi, that would give me the 7 pi. But more importantly is the fact that both of them will reduce with the 12. So 4 twelfths, because we're going to have the sine of this sum, so 4 twelfths is 1/3, so it's really pi over 3, and 3 twelfths is 1/4, so it's pi over 4. Now we have two angles that we can get the sine and cosine values of. So we have the sine of a sum, so this is going to be the version of the formula we use. If we have a plus here, we have a plus here when dealing with the sine sum. And then it's just a matter of substitution. In our case here, pi over 3 is going to be u, and pi over 4 is going to be v. So sine of u is sine of pi over 3. Cosine of v is cosine of pi over 4. Then we have the plus. Cosine u is cosine pi over 3. And sine of v is sine of pi over 4. Now, by now, you should hopefully know these values. You should know all of your quadrant 1 values by now. If not, start studying them a little more. Because if you don't know them, that's okay. You can go do a little side work. You can draw a triangle. You can figure out what the value is. But you should know by now that the sine of pi over 3 is root 3 over 2. The cosine of pi over 4 is root 2 over 2. And then we have our plus. Cosine of pi over 3 is 1/2. And the sine of pi over 4 is square root of 2 over 2. So hopefully you know those values by now. And cleaning this up a little, we multiply those two together to get root 6 over 4. This would give us root 2 over 4. So that when we add the two of those together, if we wanted to make it a single term, then we combine the like denominators and we have root 6 plus root 2 all over 4. And we're done. Looking at the next example, we're going to get to solve an equation. And here we have cosine of 2 theta plus 3 equals 5 cosine of theta. And they want the answers between 0 and 2 pi, including the 0 but not including the 2 pi. So within the first period of cosine. All right, one thing that jumps out at me with the problem right away is the fact that our arguments are the same. We have one trig value, or one trig function, which is good, but we have different arguments. So we need to find a way to make our arguments the same, and this is where that double angle formula is going to come in handy. So cosine of 2 theta, that doesn't help me if I'm going to be working with cosine of theta. So of the three choices I had for cosine of 2 theta, only one of them was solely in terms of cosine. So I'm going to choose this one. Cosine of 2 theta is equal to 2 cosine squared theta minus 1. And I make that substitution. And then the rest of the equation remains the same. Now you'll notice that the cosine is squared, but the 2 cosine squared, and you have a 5 cosine is a linear term, so this is going to end up being a quadratic, which our plan of attack should be to set it equal to 0 and then factor it. So moving everything over to the left side, I bring the 5 over, it makes it -5, combine the constants, and I should get that quadratic equation. Which of course our first attempt should always be to try to factor it. And normally, since we have a leading coefficient that is not equal to 1, we would normally say 2 times 2 is 4. I want factors of 4 that add up to -5. Use those values to break up the middle term into 2 terms, and then we can factor by grouping. But I want to also show you with a little bit of logic, sometimes you can do things a little faster. So I'm actually going to go straight to the double bubble, even though we don't have a leading coefficient of 1, because what we do have are not many choices for our factors. In other words, the only integers that you can multiply together to get a product of 2 is 1 and 2. So here for 2 cosine squared, my only choices are 2 cosine times cosine. Multiply those two to get 2 cosine squared. Likewise, for our constant here, the only way you can get the number 2 is 1 and 2. But we do have to pay attention to the signs, of course, and that's sign being SIGN. The positive on the constant means that these two numbers are going to have the same sign, SIGN that is, and the sign of the linear term in the middle is going to tell you which sign that is. So both of these are going to be negative. A negative times a negative is a positive, and then the sum of two negatives is going to be negative. So with playing a little bit of playing around with it, you should be able to figure out that 2 times 2 would be 4, and 1 times 1 would be 1. If you add them together, you get your 5. So we have -1 here and -2 here, and double checking for the middle term. 2 times -2 is -4. -1 times 1 is -1. Add them together, you do get your -5. So now we're going to use the zero product property. Anytime you have two things multiplied together and the result is 0, that means one of them must be 0. So either the first factor is equal to 0, or the second factor is equal to 0. Now we can solve each equation individually. On the first one, I'm simply going to add 1 to both sides, which gives me that. And divide by 2 would give me cosine of theta equals 1/2. Or in other words, a function of an argument equals a value. Now from here, we want to figure out what is the argument whose cosine is going to be 1/2. So starting with that, we're going to look at the triangles, and notice how the cosine is positive. So that is going to happen either in quadrant 1 or in quadrant 4. In order for cosine to be 1/2, that means adjacent over hypotenuse would have an adjacent of 1 and a hypotenuse of 2, this being our angle. And hopefully now you recognize a 1, 2 square root of 3 triangle, which is a 30, 60, 90. My angle, theta, which is right here, is opposite the root 3, the longer leg, so that makes it the longer of the two, or the larger of the two angles. So it's going to be opposite the 60-degree angle. And then for the radians, of course, that is going to be pi over 3. So our first angle here is pi over 3. Our second angle, which will have the same values for the triangle, still a 30, 60, 90 triangle. But this one, we're measuring the angle from the initial side to the terminal side. So measuring it this way means we can think of it as all of pi over 2, and then minus that 1/3, which gives us 5/3. So it would be 5 pi over 3 would be our second angle. And those are the two arguments where if you take the cosine of it, you're going to get 1/2. Now for the other equation, of course we add 2 to both sides, so we have function of an argument equals a value. Cosine theta equals 2, so the question is, what is the angle whose cosine is 2? Well, if you think about the graph of cosine, it's always going to give you values between -1 and 1. It's never going to come up here and hit a value of 2. So therefore, this equation has no solution to it. So we can ignore that one and focus on these values. And since they only want answers between 0 and 2 pi, then we don't need to write it as a general solution. So these end up being all of our solutions. So therefore, our solution set would be pi over 3 and 5 pi over 3. And we're done with that one. Now for the last one, I'm going to show you a little more with the substitution. Let's say we have this equation, and again they're asking for solutions between 0 and pi over 2. Now we had a similar problem in a previous section where it was sine times cosine equals 0, which then we could treat it using the zero product property. However, this time we can't manipulate the constant over here so that we get it equal to 0, being something that we could factor. So what we're going to have to do is look for another way to deal with that. And if we remember our double angle identities, the sine of 2 theta is equal to 2 sine theta cosine theta. So if I multiply both sides by 2, that would give me this equation. And then hopefully we recognize the opportunity to make that substitution. So this expression on the left is equal to the sine of 2 theta. So now I have function of an argument equals a value. Although my argument is no longer just theta, I do have it in the form that we can deal with. So if we think about the question, what is the argument whose sine is -1? Well, think about the period of sine. This is one period of the sine curve. And the only place it ever is a -1 value would be right here, which is at 3 pi over 2. Now that's not our angle, that's our argument. The sine of 2 theta is our equation. So the rule here is anytime your argument is something other than just theta, then you have to use the general solution and then start plugging in values of k to find your specific solutions, or in this case the ones between 0 and 2 pi. So for our general solution, the format is the argument is equal to the angle plus the periodicity. Notice how the argument here is just what you're taking the sine of. The angle is the one that satisfies this equation. And then the periodicity depends upon the function. Since we have sine, we're using 2k pi. And now just divide through by 2 to solve for theta, and you'll get theta equals 3 pi over 4 plus k pi. So what we want to do here is start plugging in integer values of k to find thetas that will be between 0 and 2 pi. So in other words, when we do plug in values of k, we're going to find that theta will be between 0 and 2 pi when k is either 0 or 1. Or using a little bit of logic, we can build our solution set as follows. We're going to say that, therefore, our solution set is going to be, now if we think about -1 as a value for k to start out with, notice how you'd have 3/4 minus 1 would have a negative value for our pi, and negative is less than 0, so that won't work. And anything that's more negative ends up being even further away from 0. So no negative value of k is going to work. So we're going to start with 0, and if we use 0 for k, then this term goes away, and it just leaves theta being 3/4, which is our first answer. Now, our next answer, we look if k is equal to 1, then I have 3/4 plus 1 is 3/4 plus 4/4 is 7/4. So that would be 7 pi over 4 is our second answer. And we keep going until we find a value that is larger than 2 pi. But if we look at the very next one, if k is equal to 2, then we already have 2 pi. So 2 pi plus anything would put you larger than 2 pi. So ends up that these are our only two answers, and we can complete our solution set. So therefore, the solution set is 3 pi over 4 and 7 pi over 4. And we're done.